Hello everyone, in this video we're going to be talking about how to determine the acidity of an acid using a qualitative approach. We learned about how to use the pKa values to determine the acidity, but let's suppose you don't know the pKa values and you still got to compare two acids to determine the acidity. In that case, you can use the qualitative approach. So in ARIO effect, you're going to be looking at four different factors. The first one is the atom effect, resonance, inductive, and orbital. So we'll look at those one by one. And as far as the ranking go, they roughly follows the same order. Like the atom effect predominates the resonance effect, and that dominates the inductive effect for the most part. Not always, however. So in order to determine the acidity of an acid, we're going to be focusing on the stability of the conjugate base. So suppose I have this acid HA. I want to be able to quickly write down what the conjugate base is going to look like. So at this point, without even writing the equation, what would be the conjugate base of that acid? Well, it's going to be A minus there. All right, so I can go ahead and write down all the electrons there. Now, how stable this conjugate bases, that's going to be the determining factor on the acidity. So if you have a stable conjugate base, so more stable the conjugate base, more acidic the acid going to be, and vice versa. So you have less stable conjugate base, then your acid is going to be less acidic. Now, how do you really determine when this conjugate base is going to be stable and when this conjugate base is going to be not so stable? So we're going to be looking at four different factors one by one. All right, so the first factor or the first effect is called an atom effect or an element effect. The element effect is going to take into place or takes into consideration whenever the conjugate bases that you're comparing will have the negative charge on different atoms. All right, and I can take in a couple of examples here. There's two ways you're going to be looking at. The first thing you want to look for if your atoms that you're comparing that got a negative charge, if they are from the same period or they are from the same group. So there's two different factors, two different reasonings going to be behind those two. If your atoms that's bearing the negative charge are from the same period, then your electronegativity matters. So whoever is more electronegative is going to be the most stable conjugate base because it's most likely to retain that negative charge, and as a result it's going to be more stable. And keep in mind that's only for the period. So let's take an example here. So I got a bunch of these protons written out, and we're going to be focusing on only one of the protons at a time. So suppose I'm looking at this proton right there. On the second compound, I'm looking at this proton, and the third compound, I'm looking at this proton to determine the acidity of those respective ones. And if on the first one and the second one, we do have other protons like this one right there and that one right there, they're the same as the other one that we just have picked. Be able to go ahead and draw out the conjugate bases. So it's probably going to be a good idea if you can pause the session and draw the conjugate bases of all these three compounds. So let me just move that a little bit onto the right side. So the conjugate base of this first one is going to have a negative charge on the carbon, and we're still going to leave those two protons there. We're not really taking those out. And the conjugate base of this second one will have a negative charge on the nitrogen. And then the conjugate base of this third one, and we can probably number those as 1, 2, 3 here. So I'll write those down in a minute. So let's call that, or maybe call this A, B, and C. And then call these conjugate bases as A prime, B prime, and C prime. So now we know all these conjugate bases has the negative charge on different elements or different atoms, and those atoms that we're comparing, like in case of A prime we got carbon, in the case of B prime we got nitrogen, and in the case of C prime we got oxygen. So those elements are actually in the same period, and in that case the electronegativity matters. So whoever is the most electronegative out of those three elements will likely to have the negative charge better than the other one, and as a result it's going to be more stable. So when I'm looking at your stability of the conjugate base, I'm going to be saying, okay, your C prime is going to be the most stable, then B prime, and then your B prime is going to be more stable than A prime, and that's because oxygen is more electronegative than the nitrogen, and nitrogen is more electronegative than the carbon. And as a result, your acidic strength, how that's going to behave, your acidic strength is going to be, since whichever is the most stable conjugate base, the acid of that conjugate base is going to be the most acidic. So as a result, C is going to be most acidic, followed by B, and then B is going to be more acidic than A. So that's how you're going to be determining the order of the acidity when you are in the same period. Now, what happens when you're not in the same period, but rather you are in the group? And I can take in a very generic example, something like HF, and we got HCl, HBr, and HI. Now, go ahead and be able to write down their conjugate bases. So that's going to be F minus there. And we got Cl minus, Br minus, and I minus. We know the conjugate bases we have here, they all are different elements. And now the next question you want to ask yourself, if those elements are coming from the same group or on the same period. Well, these fluorine, chlorine, and bromine iodide, they are actually in the same group. As a result, size is going to matter. So whoever is going to be bigger in size will be able to handle the negative charge better than the ion that's going to be smaller in size. So when we're looking at the size order here, I know the iodine is going to be the biggest, followed by the bromine, followed by the chlorine, and your fluorine is actually going to be much smaller than the rest of these guys. Now, in terms of the stability order for conjugate base, so bigger the base, the better you are in terms of handling the negative charge. So your I minus, I'm not going to write down the electrons there, is going to be the most stable conjugate base, followed by um, Br minus, and then you got the Cl minus, and your F minus is going to be the least stable. And as a result, what's going to be your acidic order, or the order of acidic strength? You know HI is going to be greater than HBr, than HCl, and your HF is much less acidic than the rest of these guys. And turns out these first three, the HI, HBr, HCl, they are in the category of strong acids. HF is not in the category of a strong acid. But if you're comparing among those four, HI is going to be indeed your strongest acid in this particular case. Well, let's try one more. Suppose I have H2S and H2O. So I'm trying to compare who is going to be more acidic between those two. So before you do anything, go ahead and draw out the conjugate bases of those. So the conjugate base of those two is going to be SH1 minus, so sulfur is getting the negative charge, and then the OH minus there. Between those two, I know in one case I got the sulfur getting the negative charge, and in one case we got oxygen getting the negative charge. And since we're still going to be in the atom effect, this oxygen and sulfur are going to be in the same group, so your size is going to matter. So who is going to be bigger in size in this particular case? Well, sulfur is below oxygen in the periodic table, so it's going to be bigger in size. As a result, when you look at the stability, SH1 minus is going to be more stable than the OH1 minus, and as a result, your H2S is going to be a stronger acid compared to the water. So that's how you're going to be looking at the atom effect. Now, suppose the atom effect doesn't really help you, and in that case, you got to look at the resonance effect and inductive effect. So let's talk about the resonance effect first. So I got a couple of these examples here. So suppose I have these two comparisons needs to be made here. Going to be looking at these two guys here. So go ahead and draw out the conjugate bases of both of those. So the conjugate base of the first one is going to look like this, And the conjugate base of this second one will look like this. Now, the atom effect is out of the question here because in both of those conjugate bases, oxygen is the one that's getting the negative charge. So since the atom effect is out of the question, now you look for if you have a resonances or inductive effect. And here we focus on the resonances. Well, there is really not any resonance for this first one because I can't really move this lone pair anywhere. Like if I try to do that, then this carbon right there is going to have 5 bonds. So you really can't do that, okay? So there's no resonance on this one. However, there is going to be a resonance onto the second one because you can move this lone pair and that pi bond between the carbon and oxygen can relocate onto the oxygen there. And this oxygen lone pair is also going to be the allylic. That's just another name for it. So as a result, you get a new resonance structure where this top oxygen is going to have a negative charge now, and then this oxygen on the right side will have a double bond. So more resonances you have, more stable your conjugate base going to be. So that's how we're going to be looking at it. More resonance structure of conjugate base, more stable it is, and as a result, acid of that particular conjugate base will be more acidic. Since we don't really have any resonance for the first one, we got the resonance for the second one. So the acidity of the second one is going to be greater. So I can say this is going to be more acidic than the first one. And if you recall the pKa values, like if you don't have to memorize the pK values for every single one, but if you do recall the pKa values, this is an acidic acid where the pKa of acetic acid is about 4.74, and the pKa of alcohols is about 16. So we know based off the pKa's as well, but then if you don't remember the pKa's, sometimes you will not have the pKa's of every single thing, and that's why you got to rely on the qualitative approach to figure out the acidity. Okay, let's try this next one here. It's probably going to be a good idea if you can pause the session and figure this one out on your own. So I assumed you guys did pause the session here and figured out which one is going to be more acidic. And let me try to do this one here. So I want to go ahead and draw the conjugate bases of these guys. So I will just copy this down actually. So the conjugate base of this first one will look like this. And how would the conjugate base of the second one will look like? Well, just get rid of the proton and see how it looks like after that. So you're going to have a negative charge on the oxygen in both cases. However, this particular electron pair is kind of a benzylic, or you can say it's going to be resonating in the ring. So I can have a multiple resonance structures where this can go in here and that can come out. And now it's just a matter of drawing multiple resonance structures. So if I just for the sake of time, I can just copy that down and I'll erase a part of it. So when you do go ahead and make a double bond there, your negative charge is going to be right there. And then you can keep going until you kind of come back to the same resonance structure. So this can move in there and that pi bond breaks in and it will restore the negative charge on this new carbon location there. And I can go ahead and copy this one down as well. So when you relocate that, we'll have a double bond right there, and we're going to have a negative charge right there. And then I can go ahead and move this lone pair again because that's going to be in conjugation with the next double bond there, and that will come out on here. So you'll get another resonance structure here. So I'll copy that down as well. So now it's going to look like the double bond on the right side stays the same. You're going to have a new double bond right there, and then you're going to have a negative charge right there. So this can come down here, and the pi bond between the carbon and oxygen break, and that electron density goes back onto the oxygen, that will go back to the first structure that we got there. So you do have multiple resonance structure for this particular one, but when I'm looking at the second one, we don't really have any resonance structure. There's no way for that oxygen lone pair to go anywhere, so there's no conjugated double bonds or pi bonds around. And as a result, since there's no resonance, this is going to be less stable. And the conjugate base on the top is, because of all these resonance structures, is going to be more stable. So the more stable conjugate base will give you the most acidic acid. So this first one right there is going to be more acidic right there. And if you look at the pKa values, the phenols, the pKa is about 9 to 10, and alcohols pKa is about 16. So there is a quite difference in the pKa values as well. And like I said, if you don't remember the pKa's, that's why you got to look at this qualitative approach. Well, let's try to do another one there. We're focusing on these two protons. It's probably going to be a good practice for you guys to figure out if which one is going to be most acidic. So I'll call this proton 1, and we got another one here that I have labeled. Call this proton 2. Um, so which one is going to be more acidic? Well, before you do anything, make sure you draw the conjugate bases for both of those. So if I draw the conjugate base for this first one, I'm just going to duplicate that here. So after losing that to one proton, I'm going to get a negative charge on this nitrogen. That nitrogen already had a lone pair, so we'll get another lone pair because that bond or the proton has gone away. That's one of the conjugate bases if you lose that proton 1. But what if you lose the proton 2? So when you're losing the proton 2, let's see how that's going to look like. So I'll just draw that down here. Okay, after losing the second proton on the other nitrogen there, you get a negative charge on that particular nitrogen. So clearly in both of those conjugate bases, I'll call this conjugate base 1 prime, and I'll call this conjugate base 2 prime. And in both of those conjugate bases, we have nitrogen with the negative charge. So atom effect is out of the question. So now you look for if there is any resonance. Do we have any resonance for the case of conjugate base 1 prime? Well, clearly we do, because this lone pair is allylic with respect to that double bond, or the double bond between the carbon and oxygen. So the lone pair on that nitrogen can go in there, and that can kick out to restore the electron density on that particular oxygen. So I could have another, so move that a little bit down here. I will have another resonance structure of that, and that would look like this. Got a double bond on the nitrogen now, and extra lone pair on that oxygen with a negative charge. And I'll just draw an arrow there showing the resonance structures. But what about this second conjugate base here, which we called it 2 prime? Do we have any resonance structures for that? Well, this lone pair, or this nitrogen, is not conjugated with that double bond because it's too far away. There are, if I draw the bonds in this particular case, there are actually 2 sigma bonds before you get to that double bond. So they're not conjugated with one another, or another way of saying they're not allylic with respect to that pi bond, and as a result, they are not going to be conjugated. So there is no resonance for this particular one. So since there is no resonance for that particular nitrogen conjugate base, that one is going to be less stable. And the conjugate bases that we have drawn up there, and we would including the resonances, that's going to be more stable. So since they are more stable, this proton right there is going to be more acidic proton. So that's how you're going to be determining if you have a less acidic or more acidic proton in the same compound. Okay, suppose your resonance doesn't really help, or sometimes you may have the same number of resonance structures, and that will not help in that case, and that's when you look for the inductive effect. And in inductive effect, you're going to be looking at if you have electron withdrawing groups or the halogens. The halogens are also kind of act as an electron withdrawing groups, or if you have an electron donating groups. So the thing about electron withdrawing groups, they're going to be withdrawing the electrons onto themselves, and that's going to be stabilizing the conjugate base. How does that really work? Suppose I got a conjugate base that has a minus charge on here, and that's attached to a close by electron withdrawing group. So what's that going to do? It's going to withdraw the electron onto itself, and when it withdraws the electron onto itself, it's going to decrease the electron density on that A atom. So as a result, this becomes more stable. But the opposite is going to be true if you have an electron donating group. So electron donating groups, what they do by nature, they donate in the electrons on to the other side. So this atom A already have a negative charge, and now what are you doing? You're putting in more electron to where you already have an electron rich region. So that as a result, that will become less stable. So keep in mind your electron donating groups are bad for the acids. The electron withdrawing groups are going to be good for the acids. And it's going to be opposite when you talk about bases. Like if you're trying to determine the basicity of a base, you actually want to have an electron donating group so that you can have all the electron pair on a particular atom concentrated. So let's talk about an example here. So suppose I got an acidic acid, and I'm going to be comparing this acidic acid with a trifluoroacetic acid. So in a trifluoroacetic acid, it's going to be everything be the same in terms of the functional group, but then you're going to have three fluorine atoms on it. So since these fluorines, halogens, they are electron withdrawing groups, so this is going to be the trifluoroacetic acid or TFA. What it's going to do, it's going to be pulling in the electrons onto this itself. And before you actually come down to the inductive effect, go ahead and draw the conjugate bases of those. And the conjugate bases of both of those, and I may not draw both of them actually, will have the same number of resonance structures. That's how it's going to look like for the first of them, and for the second one, that's how it's going to look like. So if I want to draw the resonance structures, this can go in there and that can come out, and the same story on this left conjugate base that can come out. So you will have two resonance structures in both cases. So your resonance structure is not going to really help here. As a result, you look at the inductive effect. So fluorines, what they're going to be doing, they're going to be pulling in the electrons like this. There's going to be an inductive effect pulling in the electrons, making this more stable conjugate base. So since they make this particular one more stable conjugate base, the acid of that is going to be more acidic. So this one is going to be more acidic. Okay, but on the other hand, if you have an electron donating group, so I have a very similar example here, but now I got these R groups. Well, before I get down there, some of the common examples of electron withdrawing groups are going to be like your halogens, obviously. But in addition to halogens, you also want to be familiarize yourself like NO2 and CN, the cyanide groups. And then there are some other electron withdrawing groups that you will learn later on. But for right now, if you just kind of memorize, nitro is kind of very commonly seen in including the cyanide and halogens as well. But you will have some other electron withdrawing groups when you talk about organic chemistry later on. Okay, let me make some space here. Okay, let's look at this problem here. So we have actually different types of halogens now, same functional group. So when you have multiple atoms or multiple halogens, you're going to have to look for obviously the most electronegative, and the second thing you want to look for is who is going to be the closest in that case to your functional group. So if I call these 1, say 1, 2, 3, and 4. I can clearly see that you're going to have two fluorines on the fourth one, so that's going to have the greatest inductive effect, and the three is going to have chlorine that's less electronegative than the fluorine, and then obviously bromine is even less electronegative. So when I'm writing those electronegativity orders, I know fluorine is more electronegative than chlorine, which is more electronegative than bromine. And since we have two fluorines on this fourth one, this is actually going to be the most acidic because we're going to have the most inductive effect in this particular case. And when I'm looking at something to be the least acidic, well, it's going to be the one with bromine because you're going to have the bromine being the least electronegative. So if I want to go ahead and order those in the acidic strength, your 4 is going to be the most acidic, followed by 2, because now in 2, you got fluorine that's going to be more electronegative than chlorine and bromine, and that's going to be 2 is going to be more acidic than 3, and your least acidic in this particular case is going to be the bromine, or 1 technically. Now, if I have an example where suppose I'm getting, I'll just copy this down, I got this thing right there versus, I'll just get another one of those. But now in this second case, your fluorine is actually a little bit further away from the functional group. So as you move away from the functional group, your inductive effect also decreases. So you're going to have a stronger inductive effect for the case of this first compound, and you're going to have a weaker inductive effect for the second one because fluorine is kind of moving away, or fluorine is far away from the functional group. So as a result, this first one is going to be more acidic. As far as your electron donating groups go, all your alkyl groups are going to be electron donating groups, or like R groups, basically ethyl, methyl, propyl, and then you will have some other electron donating groups, like I can talk about alkoxy group, which are like OCH3, or like I'm in generic way of saying it's going to be OR. Now in this particular case, everything else is the same. You got an carboxylic acid functional group there. They're all going to have two resonance structures. So, okay, if I want to go ahead and draw out the conjugate bases for these guys, this is how it's going to look like. And I can probably just copy these down here. And with the only difference, we're going to have another methyl group here, and we're going to have two methyl groups there. So more alkyl groups you have, more electron donating nature it's going to be. So if I look at the second one, so let's call this 1, 2, and 3. If I look at the second one, you got an extra alkyl group or a methyl group there, and that's going to be the electron donating in nature. But then when I look at this third one, we got 2 now. So you're going to have more electrons being donated into that negatively charged center. As a result, this is going to be less stable. But this first one, if you use that as a reference, there's really nothing else attached to that particular carbon there. So this one is going to have the least electron donating character in there, and that's going to be the most stable. So if that's the most stable, this guy is going to be the most acidic out of all of them. Okay, let's look at this practice problem, and it's probably going to be a good idea if you can figure out what's really going on in terms of the acidity here, is we can focus on only one of these protons right there, so that's attached to the oxygen atom, and we can go ahead and draw out the conjugate bases on all of those, and obviously the best way to do it, I can just copy this down and put this down here. So when I do so, I can go ahead and take out all these protons here. And each one of those conjugate bases will have oxygen with a negative charge. And it seems like you may have a very similar number of resonance structures in here as well. And just for the naming purposes, or just for calling those easily, I can call this 1, 2, 3, 4. You can clearly see that 2 seems to be a reference because on that particular position you have only hydrogen there, but in the rest of these guys you have this metal group on the first one, and then you have the ethoxy group, or methoxy group rather, on this third one, and then you got this nitro group. And just by knowing the natures of these different substituents, we know the nitro is going to be your electron withdrawing group, your alkoxys are electron donating groups, and your methyl is also going to be electron donating groups. So when you have multiple electron donating groups, you're going to have to figure out who is actually a stronger electron withdrawing group. And nitro is an electron withdrawing group because of the resonance as well. So I'm not going to draw the resonance for all of those, but if I focus on the resonance of this second one, so let's see how that's going to look like. And just copy this down here. Make a little bit of space here. Okay, so what's going to happen? I can have this moving down here to create the double bond between the carbon and oxygen. This pi bond breaks and get the electron density on that particular carbon. So let me just copy this down just for the sake of time here. So you got a double bond here, and then I got a negative charge right there, and I can just keep going around. Let me copy multiple of those. So when I go in the next step, I can have this lone pair going in there and that double bond coming out here. And now you can clearly see that where you have um, all those R groups attached, that particular carbon is about to get a negative charge. So this is getting a negative charge right there, and obviously you can go around and move this lone pair onto this next position, and that pi bond comes out. Um, However, in all of those cases, the most important resonance structure is going to be this, let's call this A, B, C. The most important resonance structure is going to be B. The reason why B, because that carbon that has multiple other groups like methyl, methoxy, and nitro is the one that's getting the negative charge, and then you have to kind of think of how that's going to be a factor in those particular cases. All right, so then when this goes back in there, you're going to have your first resonance structure. Now, if I just focus on this B, and if I go ahead and draw this particular resonance of all other conjugate bases, then this is what we're going to be looking at. So I'll just clean that a little bit, but let me copy that down here. So this is the one that's getting the negative charge, and I'm going to make a couple of these copies here. Okay, so for the first compound where you have a methyl group, I'm going to have a methyl group attached here. For the second one, there is just a hydrogen. And for the third one, there is a methoxy group. And then on the fourth one, there's a nitro group. So this is how the nitro group looks like, actually. Minus charge there, and a positive charge on that nitrogen. I'm going to call this 1 prime. That's what we called them up there. 2 prime, 3 prime, and 4 prime. We can clearly see that this 1 prime is going to be donating in the electrons because of its donating nature of the methyl group. So that's going to be destabilizing that negative charge. While the second one is just a reference because you have a hydrogen. The same can be said about this 3 prime because the alkoxy group are electron donating in nature, so it's going to be donating in the electrons, and that's going to be making that negative charge less stable. But when we look at this nitro group, the nitro groups are electron withdrawing due to the resonance because I have this negative charge, or a lone pair of electron, and right next to that negative charge, I got a nitrogen with a positive charge. So you can move this particular lone pair right here, and then you get this extra resonance structure. So since you get this extra resonance structure, that makes this particular conjugate base even more stable. So more resonances you have, more stable your conjugate base is going to be. That's how we have been talking about. So let me just go ahead and redraw that. So this is where you're going to have new double bond created, and then you're going to have a negative charge on that particular oxygen. So since you're making this extra resonance structure, this makes that particular conjugate base containing the nitro group more stable, and as a result, the acid of that particular um, the acid of that particular conjugate base is going to be the most acidic. And just for the order purposes, I would have 4 to be the most acidic, followed by 2, because that's just reference. There's nothing attached to it. Just have the hydrogen, and then you have 1, because in 1 you have a metal that's less electron donating than the methoxy group, and then your 3 is going to be the least acidic in that particular case. Finally, the last thing we look for is the orbital effect. If you have a proton that's attached to an sp carbon, is going to be more acidic than the proton that's attached to an sp2 carbon, and that's going to be more acidic than a proton that's attached to an sp3 carbon. And if I take examples here, so suppose I got a triple bonded compound. So you have a terminal alkyne where you're going to have a hydrogen there. And then I can talk about a double bonded proton. And then we can obviously have the alkane. So I can just, as a reference, draw out one of those protons here. So we're looking at this proton, that proton, that proton. Now the difference between those 3 protons is this carbon in the first one is sp, this carbon in the second one is sp2, and the carbon in the third one is sp3. So more S character you have, better you are in terms of handling the negative charge once the proton goes away. So in sp you have a 50% S character and 50% P character. In sp2 you got 33.3% S character, and then you got almost 67 66.7, but something like that, P character. And then in sp3 we got 25% S character and 75% P character. So more S character you have, closer you're going to be closer you're going to be toward the nucleus, and the nucleus having the positive charge will be able to handle the negative charge better. And as a result, these are guys going to be, this proton is going to be the most acidic, and your alkane is going to be the least acidic in that particular case. And if I go back and recall the pKa values of those, the pKa value of alkynes is about 25. The pKa of your alkenes are going to be about 44, 45, and then pKa of your alkanes is going to be greater than 50 or somewhere around 50. So those are your 4 factors you're going to be looking at. If you have any questions, feel free to leave any comments in the section below.